everyone. This is Jesse Crawford with New York Medical College, and this is going to be the supplemental lecture for Anova, which stands for Analysis of Variance. We've already talked about how you can use a two-sample t-test to compare two samples that are statistically independent. That would be a good technique to use if you wanted to compare two treatments, such as two drugs or two different types of surgical procedures. Anova is a method that generalizes that to 3 or more treatments. So if you had 4 or 5 different treatments that you wanted to compare, then Anova would be the technique to use in that situation. Alright, let's go ahead and get started with an example. Let's say you have 15 mice, and you have 3 potential diets for the mice: a standard diet, a junk food diet, and an organic diet. One thing you could do to investigate these diets is randomly divide the mice into 3 different equal subgroups with 5 mice each, and then you could feed each of those subgroups a different diet. Then you could see what the weight gain is for each group and try to figure out which diet leads to the highest weight gain, which diet leads to the lowest weight gain, and so on and so forth. Now, before you could figure that out, you really need to start with the question, are these diets even different at all? Or are they all just the same? And that's what the question in this example is asking. It says, test the following hypothesis at the alpha equals 0.05 significance level. H naught, mu1 equals mu2 equals mu3. In other words, H naught is saying that the diets are all the same. They're going to all lead to the same average weight gain. Versus the alternative hypothesis that they're not all the same. And notice that saying they're not all the same is equivalent to saying there's at least one pair that are different. So it's equivalent to saying either mu1 is not mu2, or mu1 is not equal to mu3, or mu2 is not equal to mu3. So this is the type of problem that we want to solve when we're doing an Anova problem. We have several different groups. In this case, the 3 different groups we have are the 3 different groups of mice that are each on a different diet. And we're trying to ask the question, are the means for those groups all the same, or are at least one of those pairs different? And so that's our goal on this type of problem, and we're going to look at how to solve it. So as just stated, on a problem like this, we're going to use the technique of Anova, which is analysis of variance. And in order to use this technique, we have to make 3 assumptions. Our samples have to be statistically independent, within and among groups. What that means is, if I take one group, like the standard group, the entries in that sample are statistically independent. But also among groups. In other words, the entries in the standard group are statistically independent from those in the junk food group. We're also going to assume that population variances are equal and that our populations are normally distributed. You might notice that these are the exact same assumptions that were in place with the independent 2-sample t-test. And the reason for that is that the Anova is basically just a generalization of the 2-sample t-test to multiple samples. You can almost think of an Anova as just a multiple sample t-test for independent samples. Alright, let's go ahead and get started with the Anova procedure. The first step when you're doing an Anova is to find the average of each row in the table. So if you take the average of the numbers in the standard row, you get 9.4. For the junk food row, it would be 11.6, and for the organic row, it would be 10. You'll also notice that the number 10.33 is at the bottom of the table. That's the grand mean, which means it's the average of all of the numbers in our original data set. It's also the average of the averages. In other words, if I take the 3 averages in the far right column and average those, I'll also get 10.33. Now that we've found these averages, let's proceed to finding our sum of square deviations. You'll probably remember that phrase, sum of square deviations, from lecture 2, when we were talking about calculating the variance of a data set. And you'll remember that when you were finding those sum of square deviations, you just kept taking a number, subtracting the mean, squaring that, and then adding those results together. That's what we're going to do here. We're going to take each number in the table, and we're going to subtract the mean for that row and square that answer. So in our first row, we have 9 minus 9.4 squared, 10 minus 9.4 squared, and so on and so forth. You see how we're taking all the numbers in the first row, and we're subtracting 9.4 from those because 9.4 is the average of the first row. And we're squaring all these results. Then you're going to repeat that for the next row, except in the next row you're going to use 11.6 because that's the average for that row. And finally, for your third row, you're going to take each number and subtract 10 because the average for the third row is 10. So we're just taking each number, subtracting the corresponding average, and squaring that result. The third table on the slide shows the answers that we get when we do that. So if we take 9 minus 9.4, we get 0.4. Then when you square that, you get 0.16. And that's why the first entry in the table is 0.16. And just proceed in that manner. So all the numbers in this third table are just the numerical results that we get whenever we perform the calculations in the second table. Notice in the table where it says square deviations, in parentheses next to that it says within groups. The reason for that is the numbers that we're calculating have a purpose of trying to figure out how much variability there is within each group. How much variability is there within the standard group, or within the junk food group, or within the organic group? This is opposed to a different measure we're going to be looking at it in a moment, which is between groups. The between groups variability measures how far apart is the standard group from the junk food group on average? How far apart is the junk food group from the organic group on average? So our ultimate goal with both of these types of deviations is to find the sum of squares and the mean square. The sum of squares is basically what it sounds like. It's just the sum of all these squares that we found in the last step. So we're going to take all the square deviations we calculated in the last step and just add those all together. And we get 18.4. But now we want to find the mean square, or you could think of it as an average square. How big are these squares on average? And in order to do that, we might be tempted to divide by 15 because there are 15 numbers in the table. But you'll remember that earlier in the course, in Lecture 2, when we're finding a variance, we don't actually divide a variance by n, we divide the variance by n minus 1. In general, whenever you're finding an estimate for a variability, you divide by the degrees of freedom. Now normally we think of a degrees of freedom as just being the number of elements in the data set minus 1. But here we don't just have one data set, we have 3 data sets. So our standard group of mice has 5 mice in it. So the degrees of freedom for that group is 4. Then the degrees of freedom for the junk food group is 4. The degrees of freedom for the organic group is 4. So actually we have 12 degrees of freedom here. So in general, the way you're going to find the total degrees of freedom is just take each group size minus 1 and then add those all together. So we have 4 plus 4 plus 4 gives us 12. Therefore, the mean square within groups is the sum of squares, which is 18.4, divided by the degrees of freedom, which is 12. And so we get 1.533. Alright, now that we've found our mean square within groups, as alluded to earlier, we'll find our mean square between groups. In order to do this, we're going to focus on the last column in the table, which has our average for each row, and it also has the grand mean, which is 10.33. Finding the sum of square deviations between groups is very simple. We're just going to take each of those averages and subtract the grand mean from it and square it. So, 9.4 minus 10.33 squared, 11.6 minus 10.33 squared, and then 10 minus 10.33 squared. So the second table shows you what we're actually doing, and then the third table shows you the numerical results of those calculations. Okay, let's go ahead and calculate our sum of square deviations between groups now. Now you might think that we would just add up the 3 numbers that we just calculated, the 0.87, the 1.6, and the 0.11. What we're actually going to do, though, is add those 3 numbers up and then multiply that result by 5. The reasoning for multiplying by 5 is somewhat technical, but a good intuitive way to look at it is each one of those numbers in the table doesn't just represent one observation. It represents 5 observations. For example, the 0.87 for the standard group, it doesn't just represent one mouse, it represents 5 different mice that were in the standard group. So again, to find the sum of square deviations between groups, we're going to add all those results together and then multiply that total by 5 and get 12.9. Now, for degrees of freedom, we usually think of degrees of freedom as being the number of entries in a data set minus 1, and that's going to be the case here. We have 3 numbers in the table up here, the 0.87, 1.6, and 0.11, so we just have 3 minus 1, which is 2 degrees of freedom. So to wrap things up, our mean square between groups is going to be our sum of squares, which is 12.9, divided by our degrees of freedom, which is 2, and so we get a mean square of 6.45. Alright, now that we've found our mean square between groups and our mean square within groups, we're ready to complete the problem. Remember what we're trying to do. We're trying to test the null hypothesis that these three diets are the same versus the alternative hypothesis that they're not all the same. The method that we're going to use for this is to calculate an F statistic. So F is equal to the mean square between groups divided by the mean square within groups. So for this example, our F is going to be 6.45 divided by 1.533, which is 4.21. Just like the other tests that we've done, this test is going to follow a two-step process. First of all, we're going to calculate a test statistic, and then we're going to compare it to a cutoff value in order to determine whether we're going to reject the null hypothesis or not. Now, we've already calculated the test statistic and gotten F equals 4.21, so now we just need to compare that to a cutoff value. You can get the cutoff value using a statistical table or with software. Now, if you wanted to calculate a cutoff value for a t-distribution, you would need to know how many degrees of freedom you have. For an F distribution, you actually have 2 degrees of freedom. You have a numerator degrees of freedom and a denominator degrees of freedom. This might sound kind of confusing, but it actually makes perfect sense if you go back to the formula for F. It says F is the mean square between groups. In other words, between groups is in the numerator, divided by the mean square within groups. So within groups is the denominator. So you'll recall that in the between groups part of the problem, we had a degrees of freedom of 2. So our numerator degrees of freedom is 2. For the within groups part of the problem, we had a degrees of freedom of 12. And so the within groups degrees of freedom is equal to 12. So if you look up the cutoff value corresponding to a 95% confidence level with a numerator degrees of freedom of 2 and a denominator degrees of freedom of 12, you'll get 3.89. And the rule that we're going to use for the Anova is if our test statistic is greater than the cutoff value, we reject the null hypothesis. And so that's what's happening here. We got a test statistic of 4.21. That's bigger than the cutoff value of 3.89. And so we are going to reject the null hypothesis. Now that we've completed the hypothesis test, let's think about what the results mean. The null hypothesis says that the three diets are the same. But we just rejected the null hypothesis. In other words, we're saying this data has sufficient evidence to conclude that these three diets are not all the same. The next question would be, well, if they're not all the same, which pairs are different? Are all three different pairs different? Or are two of the diets the same and is one of the other diets different? Intuitively, we might think that the junk food diet is probably leading to a higher weight gain than the other two diets, but we might still wonder, is the standard diet different from the organic diet? You can kind of see this information in the table. The junk food has a higher mean than the other two types of diets, but it's really not clear how big of a difference is necessary before we can reach a definite conclusion. So we need to conduct some kind of further tests in order to rigorously determine which of these pairs are different and which of them are the same. So now we're going to conduct the next type of test, which is called a post hoc test. Before moving on to post hoc tests, we do need to discuss how to calculate the p-value for an Anova test. You'll recall that we've already talked about calculating p-values for statistical tests involving normal distributions, and we learned that p-values are the area beyond the test statistic that we observe. Now in this problem, we just observed a test statistic of 4.21, and so that means the p-value for this test is the area under the curve to the right of 4.21. Now we're not using a normal curve here, we're using the probability distribution for an F distribution. So we're actually finding the area under an F distribution curve to the right of 4.21. It's the blue area in the diagram, and that gives us a p-value of 0.041. In order to calculate this area, you do need to use statistical software. You can do it on a TI graphing calculator using the FCDF command. Now, if you don't have the statistical software to do this, you might be wondering how you're going to get this value. Well, you can still actually get an approximation for it. So remember that the alpha value is the area beyond the cutoff value. So the area to the right of 3.89, which includes the red area and the blue area, that's equal to 0.05, because in this problem our alpha is 0.05, and so the area to the right of the cutoff value is 0.05. Now, since that entire area to the right of 3.89 is 0.05, and since the blue area is contained within that, well, then we know that the p-value here is less than or equal to 0.05. Keep in mind that since our p-value is less than or equal to our alpha value, we are going to reject the null hypothesis here, which agrees with the conclusion that we reached on the previous slide. So to make a long story short, if you have statistical software, you can calculate the p-value exactly. If all you have is a table of values that tell you what the cutoffs are, you can't necessarily calculate the p-value exactly, but you can at least say whether it's bigger than 0.05, less than 0.05. You can basically figure out a range that the p-value's in. Now let's turn our attention to the post hoc tests. Recall that our null hypothesis said that the three diets were the same, but we rejected that null hypothesis. And so now we're in a situation where we need to figure out for each pair of these diets, are those two the same or are they different? It's possible that all three diets are different, or on the other hand, two of the diets could be the same and then only one of the diets is different from those two. Since these tests happen after our Anova test, they're called post hoc tests. Post hoc is just Latin for afterwards. So these are just tests that we perform after we do the Anova, so they're called post hoc tests. So we actually just need to test every single pair of possibilities. mu1 equals mu2 versus mu1 not equal to mu2, mu1 equals mu3 versus the alternative, and mu2 equals mu3 versus the alternative. I want to mention that the assumptions in place are the same assumptions that we started with at the beginning of the Anova. These three samples are statistically independent, the population variances are equal, and the populations are normally distributed. In particular, these are not paired samples. Paired samples are when you compare a left hand to a right hand, or a husband to a wife, or a math SAT score to a verbal SAT score. In each one of those situations, the two things or the two people that you're comparing are related to each other, so they're not statistically independent. See, the mice in the standard diet are completely different from the mice in the junk food diet. There's no relationship between them. There's no pairing in place here. So these are not paired samples. They're statistically independent samples. And I just wanted to point that out because we are going to talk about testing each pair, so it could get kind of confusing. So I just want to remind you guys that even though we're saying things like testing each pair and pairwise error rate is something we're going to say later on, these are not paired tests. They are tests of statistically independent samples. On the previous slide, we just mentioned that one of the assumptions of the Anova is that all of our populations have the same variance. That's an important assumption for the Anova. And before conducting the post hoc test, we need to find an estimate for that common variance. You'll see that the formula for doing that is given on this slide. It's pretty ugly, but it should actually look kind of familiar because it's the exact same formula that we used for the pooled variance for two statistically independent samples from the last lecture, except we've just added a third sample to it, right? So it looks just like that formula, except we've added a third sample. So the first step that we're going to need to do in order to calculate this is find the standard deviation for each sample. And you can see that I've already done that here, and I've listed those numbers in the third column. Then you basically square each one of those numbers to find the variance, and then you multiply it by the degrees of freedom, add all those results together, and then divide by the total degrees of freedom. So in this problem, each one of our samples has 5 elements, so each sample has 4 degrees of freedom. So we're going to square each standard deviation and multiply it by 4. Then we're going to add all those results together. Then we're going to divide by the total degrees of freedom, which is 12. Since we have 4 degrees of freedom in each sample, we have 12 total degrees of freedom. Our estimate that we get is 1.53. Now this is an estimate for the pooled variance, but what we really need is an estimate for the standard deviation. So we can just take the square root of that number and we get 1.24. And so that's going to be our estimate for the population standard deviation for this problem. Again, the degrees of freedom on this problem was 12, and that's actually going to play an important role later in our calculation, so please keep that in mind. Alright, let's go ahead and conduct our first post hoc t-test. Here we're going to be comparing the standard diet to the junk food diet. In other words, we're testing mu1 equals mu2 versus mu1 not equal to mu2. This is really just a two-sample t-test for comparing two independent samples. So we're going to use the procedure that we learned in the last lecture to do this. The formula is going to be the same. We're going to have t equals x1 bar minus x2 bar divided by s times the square root of 1 over n1 plus 1 over n2. One thing I haven't placed a lot of emphasis on up to this point is the fact that that entire quantity in the denominator has a name. It's called the standard error. And one reason I wanted to mention it now is because on some of your homework problems, they actually just give you the standard error. So if they actually just tell you the standard error is equal to a certain number, you can just plug that number in and you don't have to go through the trouble of calculating it yourself. Now, on this problem, we know that x1 bar is 9.4. That's given to us in the pink column of the table at the top. We know the x bar 2 is 11.6. Now, S is the pooled estimate for the standard deviation that we got on the previous slide. So that's equal to 1.24. And then N1 is 5 and N2 is 5 because those are the sample sizes for our two different samples. So if you compute everything, you end up getting a t statistic of negative 2.81. Notice that the standard error is equal to the quantity in the denominator. It's equal to 0.784. So if the problem just told you that the standard error was 0.784, you could just skip immediately to the part where it says negative 2.2 divided by 0.784 is equal to negative 2.81. In any case, we've calculated our t-statistic, and as usual, we want to compare that to a cutoff value. Now, this is the main difference between this type of post hoc test and the t-test that we looked at in the last lecture. In this problem, we have 12 total degrees of freedom, and so we're actually allowed to use the cutoff that corresponds to 12 degrees of freedom, which is 2.179. So normally, if you only had two samples and each sample had 5 elements in it, well, then you would only have 4 degrees of freedom in each sample, so you would have 8 total degrees of freedom. But even though we're not directly testing the organic sample in this problem, the information that we gained is playing a role, and it's helping us estimate the standard deviation better. But let's not get too far off track. Let's just focus on what we're trying to calculate. So the two steps of the problem are calculating the t-statistic, and we've already seen how to do that, and we got negative 2.81. And then the cutoff value is 2.179. As usual, if we're in the rejection range, we're going to reject the null hypothesis. And you can see that our calculated value of negative 2.81 is well to the left of the cutoff value of negative 2.179. And so we are going to reject the null hypothesis here. Keep in mind that the null hypothesis on this problem is saying that the standard diet is equal to the junk food diet. And therefore, we're rejecting that null hypothesis, and we're concluding that there's actually a difference. And in fact, we'll further conclude, since the mean for the junk food diet is higher than the mean for the standard diet, we'll conclude that the junk food diet leads to a higher weight gain than the standard diet. As you know, anytime we conduct a hypothesis test, there's usually a confidence interval associated to it. If we're comparing mu1 to mu2, a natural thing to do is to find a 95% confidence interval for mu1 minus mu2. The formula to do this is, again, the same as the formula that we consulted in the previous lecture. Our estimate is x1 bar minus x2 bar, and then we're going to do plus or minus t sub alpha over 2 times s times the square root of 1 over n1 plus 1 over n2. Again, s times that square root, all is one entity, is the standard error. So if you know the standard error from the problem, you can just plug that in. So we can just plug in all the numbers that we know into the problem. The only numbers we don't have directly from the table are the t value, which we've already seen on the previous slide was 2.179. We would just get that from a table or using a statistical software package. And the s value, and we also did calculate that 2 slides ago, and we got 1.24. So our confidence interval ends up being negative 2.2 plus or minus 1.71, which is a confidence interval that ranges from negative 3.91 to negative 0.49. As before, one question we could ask here is this consistent with our results from the hypothesis test? And we've already discussed the fact that for a t-test, it always will be consistent. The hypothesis test led us to reject the statement that mu1 is equal to mu2. In other words, we don't believe that mu1 is equal to mu2. But if we don't believe mu1 is equal to mu2, then we don't believe that mu1 minus mu2 is 0. And this confidence interval provides further evidence of that. 0 is not in this interval. This interval ranges from a negative number to a negative number. So 0 is not in this interval. Since 0 is not in this interval, mu1 minus mu2 is probably not 0. So again, to sort of summarize that, the hypothesis test and the confidence interval are both telling us that it's unlikely that mu1 minus mu2 is 0. Or to put it another way, they're both telling us that mu1 is probably not equal to mu2, and so they're both telling us that the standard diet and the junk food diet are probably not the same. Now that we're finished comparing mu1 to mu2, we could use the same exact procedures to compare mu1 to mu3 and to compare mu2 to mu3. This slide summarizes all the results that we would get from doing that. You can see that the only hypothesis that we're rejecting is the hypothesis that mu1 is equal to mu2. In other words, this data has enough evidence to show us that the standard diet and junk food diets are different. But we don't have enough evidence to conclude that the standard diet is different from the organic diet, or that the junk food diet is different from the organic diet. You can also see on the right that we have a confidence interval for each one of those as well. This slide shows the output for this Anova problem using the statistical software SPSS. If you ever are involved in your own statistical analysis to publish some research, you'll probably be using SPSS. It's a common program that people in the social and medical sciences use. It's really nice and user-friendly. So if we just go through all the entries here, you'll see that most of these entries agree with what we've already computed. You can see that it has a sum of squares between groups of 12.9. That's what we got. The degrees of freedom was 2. The mean square was 6.46. So that's all agreeing with what we obtained. Same thing with the within group sum of squares, degrees of freedom, and mean square. All of that's the same. You can see that the F statistic obtained is 4.2. That's what we got. And the significance level is 0.041. I should mention that significance level here refers to the p-value, and that's the same p-value that we obtained earlier. Now, this Anova shows us that we can reject the null hypothesis that all the groups are the same. That's because the significance level is 0.04, which is less than 0.05. So again, a significance level below 0.05 means you have statistically significant results and you can reject your null hypothesis. But if we're rejecting the null hypothesis, then we need to look at post hoc tests, and you can see that we also have output for that. Now, if you actually look at the confidence interval for the standard to junk food diet, it doesn't actually match the confidence interval that we obtained earlier. The same thing is true for the other two confidence intervals here. And the reason for this is this post hoc test table is using Bonferroni's correction. So you can see that there's a small word above the table in red, Bonferroni. So this calculation is using Bonferroni's calculation. So we should try to figure out what that is, and that's what we're going to look at on the next slide. Bonferroni's correction comes into play whenever you're conducting a test that involves a bunch of individual comparisons. The problem with making a whole bunch of comparisons like we're doing in the post hoc tests is that if you have an error rate for each one of those comparisons, then it magnifies the overall error rate. And so the formula that we're going to be looking at is the overall error rate is approximately equal to the pairwise error rate times the number of comparisons. So looking at the example that we were just doing, our study had 3 groups, so 3 comparisons have to be made. You have to compare 1 to 2, 1 to 3, and 2 to 3. So we're making 3 comparisons. That means that if the pairwise error rate is 5%, then that actually gets multiplied by 3, and so the overall error rate could be approximately 15%. Here's another example where our study has 4 groups. Now the interesting thing is you might expect if you have 4 groups you have 4 comparisons to make, but actually we have 6 comparisons to make. We have to compare 1 to 2, 1 to 3, 1 to 4. Then we have to compare 2 to 3 and 2 to 4. And finally we have to compare 3 to 4. That means if you have 4 groups and the pairwise error rate is 5%, your overall error rate would be 5 times 6, which is 30%. On the previous 2 problems, we looked at the pairwise error rate and we used it to calculate the overall error rate. A more realistic problem is we know what our overall error rate should be. We want that to be 5%, so we need to figure out what the pairwise error rate should be. So if we have 3 groups, we have to make 3 comparisons. So if we want an overall error rate of 5%, we need to take that 5% and divide it by 3 and get 1.67%, and that would tell us what the pairwise error rate should be. One last example, if we want our overall error rate to be 5% and we have 4 groups, then we have 6 comparisons to make. So we need to take 5% divided by 6 and get 0.83%. So what this is showing is if you want an overall error rate of 5% and you have to make 6 comparisons, your pairwise error rate has to be less than 1%. So when you start making a whole bunch of comparisons in one study, you have to make the individual error rates very, very small, because if you don't, the overall error rate is going to skyrocket. We just saw that if you have 3 groups, then that results in 3 comparisons. But if you have 4 groups, it results in 6 comparisons. So you might have been wondering, is there a nice formula that we can use to calculate the number of comparisons that will happen? There actually is. If we let m be the number of groups, then the number of comparisons is equal to m choose 2. Now you'll recall this choose function from the lecture that we had on the binomial probability distribution. So m choose 2 is going to be m factorial over 2 factorial times n minus 2 factorial. And you can use software or a calculator to get this number for you. So just to go through the calculations, when you have 3 groups and you want to make a bunch of pairwise comparisons, then the number of comparisons is 3 choose 2. So that's 3 factorial over 2 factorial times 3 minus 2 factorial. So on the top we have 3 factorial is 3 times 2 times 1. In the bottom we have 2 factorial is 2 times 1. And then 3 minus 2 is 1, and 1 factorial is just 1. So all in all, we get a value of 3 there. Then if we look at the second calculation, we have 4 choose 2 is 4 factorial over 2 factorial times 4 minus 2 factorial. 4 factorial is 4 all the way down to 1. And then 2 factorial is 2 times 1. And 4 minus 2 is also 2, and so that's going to give you 2 minus 1. If you calculate that, you get 6. So this explains why when you have 3 groups, you have 3 comparisons to make, but if you have 4 groups, you have 6 comparisons to make. Okay, now that we're familiar with Bonferroni's correction, let's see how we can use it to actually calculate our own confidence intervals. Keep in mind that we usually want an overall error rate of 0.05. That corresponds to the fact that our alpha is usually 0.05. Now on our Anova example, we had 3 groups, so we're going to have to make 3 comparisons. So if we want an overall error rate of 0.05, we're going to have to divide that by 3, and that's going to lead to a pairwise error rate of 0.0167. What are the consequences of this? Well, it basically just means that when we look up our t cutoff value, instead of looking it up for an alpha of 0.05, we're going to look up the t cutoff value for an alpha of 0.0167. Now the t cutoff for 0.05 is 2.179. Again, keep in mind we have 12 degrees of freedom. But the cutoff value for 0.0167 in 12 degrees of freedom is 2.779. So if we want to calculate our Bonferroni confidence intervals, we just need to change our cutoff value to 2.779. So this slide just shows the calculation for the confidence interval when we're taking Bonferroni's correction into account. We're just using the same formula that we used from before, but you can see that towards the bottom we're using a t-value of 2.779 as suggested from the previous slide. This gives us the confidence interval from negative 4.38 to negative 0.02. And I'm not sure if you'll recall, but this is actually the correct confidence interval that the SPSS output was giving us. Let's just take one last look at this SPSS output to verify that the confidence interval that we came up with on the last slide is accurate. And you can see that it is. The confidence interval for comparing standard food to junk food goes from negative 4.38 to negative 0.02. And that's what we obtained on the previous slide. We also have the confidence intervals for the other 2 comparisons. The only comparison on this chart that's statistically significant is comparing standard food to junk food. The way that we can see that is if we look in the significance column, there's only two numbers that are less than 0.05. There's two 0.047s. Comparing standard to junk food gives you 0.047, and comparing junk food to standard gives you 0.047, but that's really the same comparison. So in summary, this Anova analysis combined with the post hoc tests said that we have statistically strong evidence that standard food and junk food diet are different, but we do not have enough evidence to conclude that the standard diet is different from the organic diet or that the junk food diet is different from the organic diet. Well, that wraps up this supplemental lecture on Anova. I hope this has helped you guys out, and as always, please let me know if you have any questions about anything. Have a good day, and I'll see you next time.